Welcome to our presentation on automating econometric workflows using Stata programming and functions. Our goal is to shift the focus from manual, repetitive tasks to creating efficient, reproducible, and reliable research. The core concepts we'll cover today are efficiency and reproducibility, which are the cornerstones of modern quantitative analysis. Imagine you have to run the same regression model for 100 different countries. Doing this manually is not only tedious, but also highly prone to copy-paste errors. Programming allows you to write the code once and have Stata run it for all 100 countries flawlessly. To understand why this is so important, let's first look at a common problem in economic analysis, the efficiency gap. Consider a typical research scenario, analyzing wage gaps across 50 states over 20 years. This is a large, complex task. The main problem is that most of the work, about 80%, is not the final regression, but the tedious process of data cleaning, formatting, and writing repetitive code. This is the hidden part of the research iceberg. This manual repetition significantly increases the risk of errors by as much as 40%, which undermines the integrity of the analysis. The necessity for automation comes from the demand for reproducibility. If your raw data is updated, your entire analysis, from cleaning to final results, should update automatically with a single click. Our goal is clear: write code once and run it infinitely. The core question we face is, how do we scale our analysis without proportionally scaling our manual effort? This flowchart helps decide the right tool for the job. If a task is a one-off, Stata's interactive menus or standard commands are fine. If the task is repetitive, involving multiple variables or numbers, it's time to use loops. A simple rule of thumb is, if you find yourself copying and pasting code more than twice, you should write a loop. This highlights that optimization begins with recognizing patterns and is key for efficiency. For values that are reused often, like file paths or control variables, macros are the perfect tool. They act as placeholders. Finally, for complex mathematical or data manipulation tasks, Stata's built-in functions are indispensable. For example, if you need to calculate the log of 20 different financial variables, instead of writing generate log var equals log var 20 times, you can use a foreach loop to do it in just 3 lines of code. These 3 tools, macros, loops, and functions, form the core of the Stata programming ecosystem. Let's explore each one. First, we have macros, which are essentially containers. They store text or numbers, much like algebraic variables such as x and y. As the quote at the bottom of the slide highlights, macros are names associated with text strings, used to store variable lists, file paths, or statistical parameters. A key insight here is that Stata treats macros as text substitution, not just variables. This is a crucial distinction we'll elaborate on shortly. Next are loops, the engine of automation. They repeat commands, acting like an assembly line robot that performs the same task over and over. Finally, we have functions, which perform transformations. They manipulate specific data points, acting like a calculator for your dataset. It's helpful to understand their hierarchy. Functions work inside variables, while loops work over variables. This means you might use a function to transform the values within a variable, and then use a loop to apply that transformation across multiple variables. For example, you could use a macro to store a list of control variables. Then you could use a loop to iterate through this list. Inside the loop, you might use a function like logof to transform each variable. Let's start by taking a closer look at the logic behind macros. The key concept to grasp is that macros are essentially aliases that perform text substitution. Stata replaces the macro's name with its content before executing any command. For example, if you define local x equals 2 plus 2, Stata first evaluates the expression to 4 and then substitutes that numeric value when you call x. However, if you define local x 2 plus 2 with quotes, Stata stores the literal text string 2 plus 2, and that exact string is substituted. This distinction between numeric evaluation and literal text storage is fundamental. We have 2 main types of macros. Global macros, which are referenced with a $sign, like $name. These persist throughout your entire Stata session. While sometimes useful, they can be risky because another do file or part of your session could accidentally overwrite them, leading to hard-to-find bugs. In contrast, local macros, referenced with a backtick and a single quote, like name, are ephemeral. They exist only until the current do file or program finishes running. This makes them significantly safer for coding and is the highly recommended best practice to prevent variable clashes. Remember, always prefer locals over globals for robust and reproducible code. Loops are truly the engine of automation in Stata, allowing us to repeat commands efficiently. We distinguish between two primary types, foreach and forvalues. The foreach loop is ideal for iterating over an explicit list of items, such as a variable list including income, wage, and GDP. It offers great flexibility, making it perfect for messy lists of strings or variables. In contrast, the forvalues loop is specifically designed for iterating over predictable numeric sequences, like years from 2000 to 2020. This makes forvalues ideal for tasks involving time series data or any ordered numeric progression. The key distinction is to use forvalues for predictable number sequences and foreach for more varied lists of strings or variables. In an economic context, these loops are essential for tasks such as applying inflation adjustments to a list of monetary variables instantly, significantly streamlining your data preparation and analysis.
Functions are essential for transforming raw, messy data into a clean, analyzable format. Think of this as a data funnel. At the top, we have raw, messy data, like Jan 01 2020 or phone 5550199. These are often imported as text strings and cannot be used directly for calculations. Through the funnel, we apply different types of functions. First, for text data, string parsing functions like substring or regexm can extract specific pieces of information, such as the digits from a phone number. Second, for dates, functions like mdy and date are crucial. They convert text dates into Stata's internal numeric date format. It's crucial to remember that Stata stores dates as integers, representing the number of days since January 1, 1960. For analysis, statistical extraction functions like r.mean or r.sd allow you to capture specific results from commands like summarize and use them in subsequent calculations. The outcome is clean numeric data, like 21916 for the date, 5550199 for the phone number, or 4.5 for a calculated average. Why does this matter? Stata cannot analyze Jan 1 2020 or phone 5550199 until they are converted to a numeric value. Here's a pro tip. Use dstring to fix numbers that were accidentally imported as text, ensuring they are treated as numeric values in Stata. This slide breaks down the core components of Stata loop syntax. First, we define a local macro named controls to hold a list of variables, age, education, and experience. This macro acts as a container for text that will be reused. Second, we initiate the loop structure using for each x of local controls, curly braces. Here, x is a temporary variable that will take on each value from our controls macro in turn. The opening brace curly braces must be on the same line. Third, inside the loop, we have our action command, summarize. This is the command that will be executed for each item in our macro. Fourth, we see macro substitution in action, curly braces x. During each iteration, Stata replaces curly braces x with the current variable name from the controls list. So first, it runs summarize age, then summarize education, and so on. Finally, the closing brace curly braces marks the end of the loop and must appear on its own line. A critical syntax rule to remember is that braces, curly braces, must be on specific lines, the opening brace with the loop command and the closing brace alone. For debugging, the set trace on command provides X-ray vision into your loops, showing each step of execution. Additionally, using display commands inside your loops can help you track progress and identify where errors might be occurring. Always start your do file with a version command. This ensures that your code will run correctly on future versions of Stata, guaranteeing reproducibility. Use log using to create a permanent record of all your commands and their output. This is invaluable for auditing and sharing your work. The preserve and restore commands are your safety net. Use preserve before any operation that changes the data, like reshaping or collapsing. If something goes wrong, restore brings your original data right back. The macro dir command is a useful utility to check which macros are currently defined in memory and what they contain. Imagine you are in a loop and need to collapse the data to get state-level means. You would preserve before the collapse, do your calculations, and then restore at the end of the loop iteration to get the original microdata back for the next state. With these foundational elements in place, let's walk through a complete practical example from start to finish.
Our task is to analyze wages across occupations using the NLS W88 dataset. The first action is to load the data using sysuse NLS W88 clear. We also define a global path macro for reproducibility. Before proceeding, it's crucial to check the data. We use the summarize wage hours command to verify the observation count, N, for key variables and identify any missing values. From the output, we see that wage has 2,246 observations, while hours has 2,242, indicating a small number of missing values for hours. The manual way to create log-transformed variables would be to write a generate command for each one. This is inefficient and error-prone. The automated way uses a foreach loop. We first define a local macro vars containing our list of variables. The loop then iterates through this list. Inside the loop, generate ln_v equals ln of v dynamically creates a new variable. For example, when v is wage, it creates ln wage. This is powerful because the same line of code works for every variable in the list. We also dynamically label the new variables for clarity, which is good practice for reproducible research. If we had 100 variables to transform, the manual way would require 100 lines of code. The automated way still only requires these 3 lines. We would just add the other 97 variables to the local vars macro definition. With our variables transformed, we can now move to the core of the analysis, running regressions automatically for different subgroups. To run separate regressions for different groups, we first need to identify those groups. The levels of union, local levels command, finds all unique values of the union variable, 0 and 1, and stores them in a local macro called levels. We then use a foreach loop to iterate over the values stored in the levels macro. Inside the loop, the regress command is run with an if condition. The if union equals I part ensures that in the first iteration, the regression is run only for non-union workers, union equals 0, and in the second, only for union workers, union equals 1. This automates the process of subsetting the data and running the analysis, ensuring the exact same model specification is used for each group. If the union variable had 3 categories, e.g., non-union, union member, covered by union, the levels of command would capture all 3, and this same loop would automatically run the regression 3 times, once for each group, without any changes to the loop structure. The primary benefit of automation is that it guarantees methodological consistency. The loop ensures that the exact same model specification was applied to both the union and non-union groups. This frees up the researcher's mental energy to focus on the economics, not the syntax. Instead of worrying about typing errors, you can focus on what the coefficients mean. In this case, the automated analysis reveals a structural difference. The return to college is significantly higher for union members, a coefficient of roughly 0.45 on callgrad, compared to non-union members, a coefficient of 0.3. Automated code requires automated safety checks. The assert command is Stata's automated quality control gate. Assert tests a condition. If the condition is true, nothing happens. If it's false, the program stops immediately with an error. This prevents your code from producing nonsensical results. The final step in any regression analysis should be to check the model's validity. Visualizing the residuals is a key diagnostic. The rvfplot command creates a residuals versus fitted plot, which helps check for issues like heteroscedasticity. The command assert wage greater than 0 checks if there are any non-positive values for the wage variable. If a data entry error created a negative wage, assert would stop the entire do file, forcing you to fix the impossible data point before proceeding. This 5-step process shows how programming can transform a manual task into a robust, reproducible, and efficient workflow. Let's summarize the key takeaways.
Thank you for joining this presentation. As a final thought, remember that programming is a crucial investment in your analytics.